So I'm out here in this park and I was wandering around vectors and vector spaces, and a question came to my mind asking what's the connection between the angle between vectors and the inner products of these vectors. I thought for a while about this and I wrote some things down, and I would like to share this to you. Okay, so we start playing with these objects we call vectors, and some natural questions will arise. We start considering two vectors, in this case vector x and vector y, in an n-dimensional vector space, and we ask ourselves, okay, what happens if we add these vectors? And by the parallelogram rule, we know that we can add those vectors just by displacing one onto another, x over y or y over x, and we will get x plus y. And similarly, we can subtract them and we will get this other vector. A common question one asks is, what's the length of this new vector x plus y, and what's the length of this new vector x minus y? And we can easily compute those lengths. We just take the components, each of one of these components, we square them and we add them up, and we take the square root of that. And the same for the subtraction of the vectors, we just subtract each component, we take all them, raise to the second power, and we just add them up and take the square root. So since we're talking about lengths, this quantity inside is a positive number because every term is squared, so we can easily consider just the length square, so we don't have to deal with the square roots. So once we square the length, we will obtain an expression like this. So a common question that emerges is, when are the length of x plus y and x minus y equal? So we are basically asking this. And well, if we know that this is equal to this, we know that if we subtract these two quantities, we should obtain 0, right? But let's just start working out this expression on the left. So if we start expanding, right, like we replace this by this and we obtain this, and then we are going to subtract this other expression here, so we subtract the whole thing, so we end up with this. And now if we expand a little bit more, this is like you have two terms square, so you just basically apply a squared plus 2ab plus b squared, and we got this. And you do this for all the other terms in the middle, and then for the last term of this vector you expand as well, and here you do the same, like you remind yourself that you have a minus in front, so you will come up with this. There are a lot of things that are going to cancel. For example, this x1 minus x1 squared, y1 squared minus y1 squared, and everything like on the edges of each expression is going to, let's say, cancel out, and we're going to remain with this thing here and these things here and the same here, all positive. So we can just combine those and we end up having this. And naturally we can define the inner product as the number. So we have two vectors living in the same like vector space. In this case, we're going to say it's an n-dimensional vector space, and we define the inner product to be the multiplication of each of the one, like each one of these, like of their entries, right? So we take x1 times y1 plus x2 times y2, so on and so forth, and the last one will be xn plus, times yn. And like if we do that, we can like basically express this whole thing as this minus like the length square of x plus y minus the length of x minus y squared will be equal to 4. The 4 comes from here, and then we replace this whole thing by just the inner product that we have defined. So another natural question that arises is, what happens if the lengths are equal, right? So what happens if this is equal to this? Well, we know that if this is equal to this, when we subtract these things, we have to get 0. We should get 0, right? But on the other hand, if we get 0 for this whole expression on the left, that means the whole expression on the right should be equal to 0 as well, because we are having an equality here, so it has to hold. But the only way this expression on the right is 0 is if this number we have defined is 0, right? Other like 4 cannot be 0. So this requires that the inner product between x and y has to be 0. And if you ask yourself, well, when does this happen? Like geometrically, we know that these lengths are the same when x and y are perpendicular. So if we have this, if x and y are perpendicular, we know that this like parallelogram that this forms is going to have same, like the length of the vector x plus y and the length of the vector x minus y are going to be the same. So only in this case we're going to have that this vector, like this length and this other length, are going to be the same. So this has like a very profound meaning, and in this case the meaning is that having defined an inner product and setting that up equal to 0 implies, but by definition, that the two vectors that we are considering are perpendicular. Okay, so we have already defined for two vectors in an n-dimensional vector space, we have defined this number and we have called that the standard inner product of x and y. And I'm sure you have seen before something like this formula or this equation, which says cosine alpha equals the inner product of x and y divided by their norms multiplied, and where alpha is the angle between x and y, right? Now the important thing, or what I want to show you today, is where does this relation comes from, right? How we have got this relation. So this is like a very basic idea, but at the same time I find it interesting. And you start setting up like two vectors in an n-dimensional vector space, and in this case we consider the vector x and the vector y, and we define another two vectors. So we define E to be the unitary vector taking x, and E prime to be an unitary vector taking y as the vector that we're going to define onto. So in this case we can like visualize E as this vector here up to here, and we can visualize E prime as this vector until here. Okay, and we have defined alpha as before. Like previously we say that alpha was the angle between x and y, and by a geometric construction or definition we know that cosine alpha is the same as the length of this vector over the length of the hypotenuse, because this is our right angle here. So we know that this is equivalent to this, and we can take out the lambda in absolute value, and since the magnitude of E and the magnitude of E prime are just 1, we have that this is equal to the magnitude of lambda. And if lambda is greater than 0, if we define it to be positive, then we obtain this cosine alpha, it's equal to lambda. But we also know that by the way we construct E and E prime minus lambda E, so we have defined lambda E to be a scalar multiple of E, so lambda E is parallel to E. And in this case we have defined, like we define E minus lambda E to be this vector. By definition we know that E minus lambda E is this vector, so we know that this vector here is going to be orthogonal to this vector here, but since this vector and this vector are parallel, this also implies that e prime minus lambda is also orthogonal to e. So we already know that being orthogonal or perpendicular is the same as having inner product equal to 0. So if we replace this if we would take the inner product of these two vectors, we should get 0 because these two vectors are orthogonal. So this implies that, if we expand a little bit, we can see that, component by component, we have this expression, and we start expanding a little bit, and here we group this we combine terms, these terms here, so we can see that this part here is just the inner product of e and e prime, and we also combine these other terms, and we can see that this is just the inner product between e and itself, and this is going to turn out to be the magnitude squared. And since e is an unitary vector, then the magnitude is 1, so the magnitude squared is going to be 1 as well. So we are going to have the following. We're going to have that lambda is equal to the inner product between e and e prime, but remember that we have defined already e to be x over the magnitude of x and e prime to be y over the magnitude of y. Hence, if we replace this here, we're going to get this. And the same, if we expand this a little bit, component wise, it will be x1, y1 divided by the magnitudes, and we're going to have the same in the middle. And then for the last component, we're going to have xn, yn divided by the product of the magnitudes. But we now realize that we can factor out in the denominator, we can factor out all these things like xy, the magnitude of that, and we're going to have just x1, y1 plus x2, y2, and so on, and up to xn, yn. So this is going to be the same as just the inner product of x and y divided by the product of the magnitudes. But we also know that lambda, as we previously defined lambda to be, we found that the lambda was equal to the cosine of the angle between x and y. So lambda is equal to this, and lambda is also equal to that. So we equate the two things, and we arrived to the expression that we wanted to derive initially. So I think it's a good construction to understand it, why the geometric meaning of orthogonality, it's related to the cosine of the angle and the inner product. And I think that's all what I wanted to show. Let me know if you want to know about anything else, and write it down in the comments, and I will check those out.